Welcome back to the deep dive. Today we are plunging into something really fascinating and actually surprisingly difficult.
Yeah. What's that?
It's the world of giving robots, well, a human touch.
Yeah.
We're looking at how researchers are trying to teach robots with these complex, multi-fingered hands.
Ah, okay, so teaching them manipulation tasks.
Exactly, just by showing them what a human does first.
Right, okay. And our source today, I believe, is a technical paper, something called DexMachina.
That's the one, DexMachina. So we're going to really unpack the engineering side, the algorithms they're using to try and get functional dexterity in these robot hands.
Got it. Focusing purely on the tech aspects.
Absolutely. And when we say challenging, it is really challenging. I mean, think about something you do totally automatically,
Like what?
like picking up I don't know, a box with two hands and opening the lid, or maybe even like handling a waffle iron in midair, flipping it, opening, closing it.
Okay, yeah, second nature for us, but for a robot.
Exactly. For a robot with one of these complex, multi-jointed hands, it's incredibly difficult.
And the core issues are, well, there are quite a few, right? You've got the huge action space.
Meaning just the sheer number of ways all those joints can move?
Precisely. An astronomical number of possibilities.
Yeah.
Then there's the need for incredibly precise contacts.
Knowing exactly where and how hard to touch the object.
Yeah, and that's especially true for articulated objects, things with moving parts like hinges or drawers.
Right.
And maybe the most fundamental thing is what they call the embodiment gap.
The physical differences between our hands and robot hands, like soft versus rigid.
Exactly. Human hands are soft, compliant. Robot hands are typically rigid with distinct joints. What works for one just doesn't map directly onto the other.
So you can't just like record my hand movements and hit play on the robot.
Nope. Not if you want it to actually work.
Which brings us to what this paper calls the functional retargeting problem. How are they defining that?
So functional retargeting, as they define it, is about learning the robot's movements, its policy, so that the object itself follows the path shown in the human demo.
Oh, okay. So it's about the object's behavior, not making the robot hand look exactly like the human hand.
That's the key distinction. Just copying the hand pose is simpler. That's kinematic retargeting. But it doesn't guarantee the task succeeds or is even physically possible for the robot. Functional retargeting focuses on the outcome for the object.
Okay, makes sense. Goal is object behavior, and focusing on these really long, complex, two-handed tasks with moving objects, that just makes all those challenges you mentioned even harder, right?
Absolutely. That huge action space, the really tricky contact sequences, and yeah, that persistent embodiment gap, it all gets amplified. Direct hand-to-hand mapping is pretty much useless here.
And this is where Dex Machina comes in.
Exactly. It's designed specifically to tackle these hard problems.
Okay, so what's the core idea? I gather it uses a curriculum, but with something maybe a bit counterintuitive, these virtual object controllers.
It is pretty clever. The name Dex Machina is kind of a play on Deus Ex Machina,
Yeah.
that plot device where some external force swoops in to solve everything.
Huh, okay. So what's the external force here?
It's this virtual controller they add in the simulation environment. Basically, it applies forces to help guide the object along the desired path from the human demo, especially early on in the learning process.
So it's like putting training wheels directly on the object the robot is trying to manipulate.
That's a perfect analogy, yeah. Initially, this virtual force does most of the work, keeping the object on track. This lets the robot's policy try things out without immediately dropping the object or failing catastrophically.
Avoiding those immediate failures, that seems crucial for complex stuff.
It really is. It's a major hurdle in training for these long sequences.
Okay, let's dig into the setup. How does the reinforcement learning environment work here?
Right, so they're working purely in simulation. They take a human demonstration or recording and pair it with the specific robot hands and the object model in the simulator.
And the robot's goal is?
The goal for the robot's policy is to learn actions that minimize the tracking error of the object's state.
Object state meaning its position, rotation.
It's exactly position, rotation, and critically, for these articulated objects, the angles of its moving parts, like the lid hinge angle, all relative to what happened in the human demo.
And the main reward signal, the task reward, basically tells the robot how well it's keeping the object on that demo path.
Yes, precisely. It measures how accurately the robot keeps the object's position, rotation, and joint angles aligned with the demonstration's trajectory over time. They combine these errors, so the robot has to get all aspects right, not just, say, the position.
But, okay, knowing what the object should do isn't enough. The robot needs to learn how to make it do that. It needs more guidance from the human demo data again.
Right. You need to process that human data to make it useful for guiding the robot's actions. First, they do an initial kinematic retargeting.
Just getting a rough guess of robot joint angles and maybe hand positions based on the human.
Yeah, a starting point. But then, and this is a key step, they showed in Figure 6, they refine this initial motion in the simulation itself.
How do they refine it?
They basically replay those initial retargeted robot hand joint movements, but they hold the object fixed in place in the simulation. If the simple mapping would cause the robot hand to, like, go through the object.
Which it probably would, given the embodiment gap.
Exactly. The simulation's physics engine gently pushes the robot hand out of the object, finding a physically plausible configuration that's still close to the original intent.
Ah, okay. So they make the target motion physically possible before trying to learn, preventing impossible goals.
Correct. They also use the human demo to figure out roughly where and when the human hand was making contact with the object. They approximate this based on distance.
And that gives them a target contact pattern for the robot to aim for.
Yes, a target for which parts of the robot hand should be touching which parts of the object and when.
Okay, so this refined motion and contact info,
Mhm.
how does that feed into the robot's actions and the rewards?
It feeds into both. They use this interesting hybrid action setup. For the robot's wrist, the 60th part controlling the hand's overall position and orientation.
Yeah.
The refined retargeted values from the demo act as a base action. The robot's learned policy only needs to learn a small adjustment, a residual on top of that.
Okay, so the wrist mostly follows the human path.
Sort of, yeah. But for the fingers, the policy learns their absolute positions directly. It has full control over the finger joints.
Why split it like that? Why not let the policy learn everything from scratch?
Well, constraining the wrist's general motion to follow the human example simplifies the learning problem significantly. It makes it more efficient. Their ablation studies, like in Figure 8, actually show this hybrid approach worked better.
Ah, okay, so it focuses the learning.
Exactly. It lets the fingers focus on the really tricky grasping and manipulation details, adapting to the robot's specific mechanics, while the wrist handles the bigger movements based on the demonstration.
Right. So you've got the main task reward tracks the object, and then auxiliary rewards based on this refined human data.
Precisely. There's ocean imitation reward that encourages the robot's hand key points and joint angles to match the refined demo data. And there's a contact reward, pushing the robot's contacts to match those approximated target contacts.
And the final reward is a mix.
Yep, a weighted sum. The task reward, object tracking, is the main driver, but these auxiliary rewards act as, like, soft guides to help the learning process along.
Okay, let's circle back to that curriculum. You mentioned it tackles catastrophic early-stage failures. What does that look like in practice?
Well, imagine that waffle iron task again. Pick it up, open it midair. If the robot's very first attempt at grasping, or its initial movement, is just slightly off,
It drops it.
it drops it instantly. The simulation episode ends. The policy gets zero reward for the complex opening and flipping part because it never even got there. It just keeps failing right at the start.
Stuck at step one.
Exactly. That's the catastrophic early failure. It prevents learning the rest of the sequence.
And the virtual object controllers fix this. How exactly do they work?
Yeah, they're the key. They use privileged information from the simulator stuff the real robot wouldn't know, like the object's exact target position from the demo. They apply forces and torques directly to the object in the simulation.
Like invisible strings pulling it?
Sort of. Think maybe more like strong simulated springs and dampers attached to the object, constantly nudging it towards its target state from the human demo.
Got it. And the curriculum part is about how strong those invisible springs are.
Right. Algorithm 1 in the paper lays it out. You start the training with these virtual controllers, really strong high gains.
So the object basically moves itself along the demo path.
Pretty much. It follows the demo path mostly on its own. This gives the robot's policy a chance to try actions, learn something about controlling the fingers without the immediate consequence of dropping the object.
Okay. And then?
Then, as the policy starts to get better, measured by its average rewards going up, the strength of these virtual controllers starts to decay exponentially.
Ah, so the training wheels gradually come off.
Exactly. The policy is slowly forced to take over more and more of the control. It has to learn the actual manipulation strategies, the right contacts, the right forces, because the virtual help is fading away.
And because the object was held stable while it was learning initially, it could actually learn the whole sequence.
That's the idea. It gets exposure to the entire task sequence from the beginning instead of getting stuck right at the start.
Okay, that makes a lot of sense. So this leads into their experiments. They built a whole benchmark platform, right?
You did, yeah. The DexMachina benchmark is a pretty significant contribution itself. It includes models for 6 different dexterous robot hands, the Allegro, Shunk, Inspire, others, and 5 different articulated objects based on a dataset called Arcetic.
And the point is to have a standard way to test these things.
Right. A unified platform to compare different learning algorithms like DexMachina, but also, really interestingly, to compare the functional capabilities of the different robot hand designs themselves.
So what did the experiments actually show? Looking at their main results, maybe figure 3, what's the headline?
The big takeaway is that DexMachina consistently, and often significantly, improved performance compared to baseline methods, especially on those really tough, long horizon tasks.
Like the waffle iron one, waffle iron 300.
Exactly that one. Picking it up, opening, closing, flipping, opening, closing again, all while holding it in midair for 300 simulation steps. DexMachina achieves much higher success rates on tasks like that.
And you can see the curriculum's impact clearly.
Oh, absolutely. If you look at the results for just using the task plus a reward setup without the virtual controller curriculum, the performance is much more inconsistent. It often fails completely on the harder tasks.
So just having the right rewards isn't enough. You need that guided learning.
It seems so for these complex scenarios, and the simple kinematics-only replay, just trying to copy the refined human motion directly,
How did that do?
basically failed across the board. Which really proves you need a learned policy that understands the physics and the contacts, not just mimicry. And the ablation studies back this up too. Figure 8 showing the benefit of the hybrid action space for the wrist. And they compared DexMachina to another method, Menib-Trans, which tried decaying physics parameters instead of virtual controllers.
How did that compare?
DexMachina's virtual controller approach was shown to be much more effective, particularly for these complex tasks. It seems to provide stronger, more direct guidance when it's needed most.
Interesting. So beyond just proving their algorithm works, using this benchmark let them compare the different robot hands functionally. What insights did they get there?
Yeah, this is where it gets really interesting for hand design. The general trend they saw was that the larger, more highly articulated, fully actuated hands.
It's like the Allegro and X hand.
Exactly. They tended to achieve higher success rates and learn more efficiently on these tasks.
So bigger is just better. More motors win.
Well, it seems a bit more nuanced than just size. Other features matter too, like the Shunk hand has actuated fingertips and a foldable palm, which seem beneficial. But the really cool part is that the learned policies adapted their strategies based on the specific hand's mechanics.
They didn't just try to do the exact same thing with every hand?
No, not at all. There are great examples. I think Figure 4 shows some. On the Notebook 300 task opening and closing a laptop, the bigger X hand tended to follow the human demo strategy. Hold the base with one hand, use the other to lift and close the lid. Makes sense. But the smaller Inspire hand, with fewer joints and different kinematics,
It couldn't do that.
it learned a different way, learned to use both hands together to sort of stabilize the notebook and carefully maneuver the lid closed. A totally different adapted strategy.
Wow.
Or, on the Mixer 300 task, the Allegro hand used its long fingers to kind of hook and manipulate parts,
Oh.
while the Shunk hand, with shorter fingers but maybe more wrist palm actuation, relied more on wrist movements to get the job done.
So the policy is genuinely figuring out the best way to achieve the goal given the specific tool the hand it has available.
That's exactly what it looks like. It's not just blindly imitating the human motion, it's learning a functional strategy tailored to the robot's embodiment.
That's really fascinating. It's learning capability.
It is. Of course, this analysis is limited by the specific objects and tasks they tested, but the framework itself, the benchmark, could be expanded to compare many more hands and tasks in the future.
Right. So thinking about the technical implications, where does this research point next? What are the big hurdles to get this kind of dexterity working in the real world?
Well, a major one is that these policies currently rely on state-based inputs from the simulation. Perfect information, basically.
Like knowing the object's exact pose.
Exactly. To work in the real world,
Oh.
robots need to handle perception, figuring out the object's state, the hand state, from cameras or other sensors. So bridging that gap, maybe through vision-based learning or techniques to distill these simulation policies onto real hardware, is a huge step.
And getting the human demonstration data itself sounds like a bottleneck.
It is. Collecting high-quality, diverse human demo data is hard. The paper mentions that maybe future progress in things like 3D generative models or better 3D reconstruction could help automate or scale that up.
And the simulation needs to be really good, right? Sim to real gap.
Absolutely critical. For real-world success, the simulation models need to capture the subtle dynamics of the real robot hardware and the object interactions very accurately. That's an ongoing challenge.
Still, the benchmark itself seems like a valuable technical contribution, doesn't it? It gives people a way to test hand designs and algorithms without needing the physical robot right away.
Definitely. It lowers the barrier to entry for research and development in this really complex domain of dexterous manipulation.
Okay, so that was quite the deep dive into DexMachina. We've seen how this approach uses that clever curriculum with virtual helpers, guided by human examples, to get robots with these complex hands to learn tricky, two-handed tasks involving articulated objects.
Yeah, tackling those early failures and adapting to different hand designs.
And how the benchmark they built is helping compare not just algorithms, but the actual functional differences between various robot hands.
It's definitely a solid piece of work pushing forward how robots can learn complex physical skills.
So here's something to chew on as we wrap up. If we can get robots to perfectly master coordinating two hands, to manipulate, say, a hinged box or a tool in simulation, something still incredibly hardball, how might that capability unlock entirely new levels of practical physical competence for robots out in the messy, articulated real world? And thinking technically, which hurdles perception, sim to real accuracy, or maybe just getting enough good training data still feel like the biggest mountains to climb on that path?